Okay, YouTube, in this video we're going to be looking at the graphs of logarithmic functions, and the fabulous thing about the graph of a logarithmic function is that it is the inverse of an exponential function. So we're going to just start with that. We're going to say, hey, the graph of y equals 2 to the x power, clearly an exponential function here. What do we remember about exponential functions? And of course, the graph has been included here, y equals 2 to the x, but things like, there is a horizontal asymptote that exists on the x-axis here at y equals 0, because we know that 2 to whatever power is never going to be equal to a height of 0. So we have this asymptote here. We can see that they grow extremely quickly. They grow really fast, and that exponential functions, they always go to this point 0, 1. And the reason why is because 2 to the 0, or anything to the 0 power, is always going to be 1. So, when we find, I guess exponential functions, we usually graph the asymptote. We graph 0, 1, of course, and we know they grow very quickly. So we plot a few more extra values here. And so what you're seeing here, excuse me, in this first table is we're plugging in -2 up to, looks like 3 here, going by ones for our x values. And we see that we get a function that it grows rapidly, okay? So when we talk about inverse functions here, we say g of x. Now g of x, I can prove it to you that it is the inverse of f of x. If f of x is y equals 2 to the x, then the inverse, let me switch colors here, would be x equals 2 to the y. And this, if I rewrite it in logarithmic notation, of course, this would be log base b, I don't want to write that box there, but base b of something turned into something here. And of course, we get our little loop around here, but our base here is 2 on our exponential expression. 2 to the power of y turns into x, and look what you have here, y equals log base 2 of x. So since they are inverses of one another, what do we know about inverses? Well, we know that their domains and ranges switch, so it says reverse coordinates. And when you look at these graphs, basically, here's what I want to point out. Logarithmic graphs are just as easy to graph as exponential functions, because if you know their inverses, then first of all, their graphs are reflected about this line, y equals x. We're reflected over this line. So what this means, reflected over y equals x. What this means for us is that our graph, if our exponential graph grows really rapidly, our logarithmic graph grows stupidly slowly, and it just always slows down. What other things? Well, if we had an asymptote, a horizontal asymptote on the x-axis, logarithmic graph here, noticing here, has a vertical asymptote on the y-axis. And then likewise, this point always is at 0, 1. This point will always be at 1, 0. And just to kind of clearly explore this 1, 0 thing, if we did y equals log base 2 of x, and of course we were making our table here, and we say x, y, and we plug in 1. Check this out, we get y equals log base 2 of 1. And one of our properties of log said, hey, log of 1 is always 0. But of course, if we couldn't figure this out on a bad day, we could do our little loop thing here. We say 2 to the power of y equals 1. This had better be a 0 here. But it's clearly awesome to know that every logarithmic graph goes through 1, 0. So logarithmic graphs, exponential and logarithmic graphs, what can be said about the domains and ranges of each of these functions? You notice that for the exponential function, its domain is negative infinity to infinity, and its range is 0 to infinity, not including 0. When we look at this graph here, kind of the maroonish graph, we say its domain is just 0 to infinity, and its range, if you look at its range, it is negative infinity to infinity. Even though it grows really slowly, it'll cover all y values for the rest of its life, starting way down at negative infinity, going up to positive infinity. So you notice that they're switched. And of course, I could write a whole lot more about that. We say that the domains and range of these functions is switched, but they're inverses, okay? And we say, how do the shapes of the graphs compare to one another? Well, can we make a little note here? We say exponential, and logarithmic. Essentially, what I want to be clear on is this. Grows, and I don't want to say it's always growth, but I'm going to say grows anyways. We say grows rapidly. It could be decay. But we say grows rapidly, and we say grows slowly. It's like molasses, man. It is just slow. So we say these graphs being what they are, let's just take a look at a situation where maybe not y equals 2 to the x and log base 2 of x. Let's do y equals 3 to the x and log base 3 of x. What I want to do is graph these both in the same window, knowing that they're inverses. So start with our exponential function. Hey, I love these because they're quick to make. Let me slow down though. We say that they have horizontal asymptotes right here at y equals 0. This is for the exponential function y equals 3 to the x. And for y equals 3 to the x here, let's go ahead and write this. We say x and I'm going to write f of x. That's this exponential function here. I'm going to plug in 0. Of course, 0 gives us 1. We know this. And I'm going to plug in positive 1 and negative 1. Now, knowing what I know about this, we say 3 to the power of 1 would be 3, and 3 to the negative 1 would just be the reciprocal of this. So we get, 1, 3 is on our graph, and negative 1, and then at a height of a third, and everywhere else it's just kind of a boring graph, we say. In here it's interesting though. So here's our exponential function, and I'm going to label this f of x. So now knowing that, we're going to have inverse functions here that are reflected over this line y equals x. I'm just going to kind of place that in here. We say, let's go graph this function here. Well, what I can tell you, just like right off the bat, is that it has to have an asymptote on the y-axis. Awesome, like awesome. Seriously, every exponential function. Let's admit this right now, or logarithmic function. It's great to know this, and also it's great to know that it goes through 1, 0. So now, in terms of our logarithmic function, I often get this question. We say, well, what are we going to plug in to this g of x here? Obviously, we would plug in 1 because 1 goes to 0, and you could obviously verify this here. But we'd say, it's good to know that it goes through this point. What other x value would you plug into this function? Well, me personally, I would plug in 3. And we're going to make a little note here. We're going to plug in an x value that equals the base. And the reason why I say this is because if we did this, if we said y equals log base 3 of, and we'll plug this in for x, we'll plug in a 3. Remember that if I were to do this, I'd really be asking the question, 3 to the power of y equals 3. What did we take 3 to the power of to get 3? Well, it had better been a 1. So the truth is always that if you plug in the base into its log, remember log base b of itself is always 1. So what this is meaning to say is that, well, this graph here would have to go through 3, 1, or its base comma 1 always. And then we could also go through, I suppose if I were to fill this in here, a third, we know that a third would go to negative 1 here. You can see how these are just switched. So a third goes down to like maybe right here, and we get this graph that comes up, and I know it's not really touching the asymptote, but it leaves, and you want it to kind of flatten out as you go. So we say g of x. So had I been making this graph a little bit more quickly here, I would have just said, hey, asymptote on the y-axis, 1, 0 definitely on this graph, 3, 1 for sure on this graph, and then kind of drawn a graph that goes up and to the right and increases slowly. So let's take a look at this here, if my screen wants to switch over here. Basically, we could see that graphs of logarithmic and exponential things are related to one another. What I have here in Desmos is kind of, you have 2 to the power, let me just have you look up over here. We say, here's our logarithmic function in red. You can kind of see this here in our exponential function in blue here, and they both have bases b. So the base being 2 at this point, you can see that this is really y equals 2 to the x, and this is y equals log base 2 of x. Clear points on both of these graphs here. You say this goes through 0, 1, this goes through 1, 0. Also, I would say that this goes through 1, 2. Obviously 1, 2 because the base is 2. This one also goes through 2, 1. And so what you can see here is in terms of, let's talk about domain and ranges, okay? Domains and ranges are switched. We have, with our blue graph, domain is left to right forever and ever. Domain is negative infinity to infinity, and range is 0 to infinity. Whereas with our red graph here, its domain is 0 to infinity, and range is negative infinity to infinity. And you can see just by changing this base here, they kind of just always behave this way. So one thing is worth noting here. If your base is bigger than 1, of course we saw with exponential functions, we call this exponential growth. Okay, what if I have a base that's between 0 and 1, like a proper fraction? So with our exponential thing, I just want to mention this here. Of course, this was a reflection over the y-axis of our exponential growth. We said that this is exponential decay. Our logarithmic graphs, instead of coming from the bottom up, come from the top down. And it confuses a lot of people. I just want to mention that here. Come from the top down, okay? And it plays off as kind of like an x-axis reflection, whereas this was a y-axis reflection. So with our graphs here, important things to note about logarithmic graphs. Log graphs, we say log graphs. We have this little table down here that's great to read through, but I just want to mention this. We say we have a vertical asymptote at x equals 0 or the y-axis. Clearly the truth. And we say we have an x-intercept at 1, 0. And they grow, and I say this loosely, grow, they could decay kind of thing going on. They grow slowly. They don't grow very quickly here. And so this table is going to kind of just break down what you see there if you want to pause and kind of read through those. But going forward here, what we're going to be doing is sketching transformations of log graphs as we do with any other function. Cheers.